not that any of this isn't pre-calculus, don't panic, analyzing graphs, specifically something called the slope, which you've heard of, and the derivative, which you may not have heard of, but turns out you've heard of. Okay, let's keep this simple. Describing graphs. If you think about a graph of your bank account over time, you'd like to see what type of situation. Well, personally, I'd like to see an increasing situation. In fact, if I was really good, I'd love to see an increasing situation constantly. That is, the balance, the amount in there, is always going up. So, when we describe graphs, talking about how it changes, increasing or decreasing, can tell you a great deal, right? One way is to talk about this increasing or decreasing numerically, and that means to use something called, well, some way of saying, okay, this is a 2 versus a -2. And you've probably heard of this. You're probably guessing, oh, wait, he's talking about the slope. And he is. Also known as the rate of change. So this is the same slope you learned about in linear equations. So knowing that, I'm going to go ahead and use m. I know, tried and true, right? We know that that's the change in y over the change in x. Now, there are certain situations where the slope itself actually represents something. So let's say I was looking at a graph where I had time, right? Let's say that's in seconds. And this measured distance. So for some amount of time, I can figure out what the distance is. And let's say that's in feet, right? Just because we're here in the US where everyone uses feet. No one else does. In any event, let's say it was pretty straightforward. Let's say I started out at a certain distance from something and I started walking away. Would you agree that the distance would increase? I bet you would. 2, 3, right? Now, that being said, there is a slope. Now, this is linear, so we know it's going to be the same slope throughout. That's not always going to be the case with the graphs we're talking about, but that means there's going to be a certain rise and a certain run, like slope triangle, right? So this would be the change in distance over the change in time. Now, by definition, that is called the velocity. And in particular, this particular velocity, because it's change in distance over change in time, the units would be feet per second. You've heard of miles per hour, right? Now this is feet per second. All right? So sometimes the slope actually represents something unto itself, in this case, the velocity. Okay, what does the slope tell you? Try not to fall asleep on me here. Positive slope, negative, 0, or undefined. Kind of covers all the bases, right? What does positive mean? Graph goes up, negative, graph go down. 0. Graph is not changing at that point, which could mean a couple of things. Either the graph is horizontal, right? Horizontal lines have a 0 slope, or it has reached a maximum or minimum. We've seen this before. By the way, when the slope is 0, we call those critical points, okay? An undefined slope occurs when the graph is vertical, undefined, or has a sharp corner. We'll explain what sharp corners and do some examples here. Well, how does now strike you? So let's say I had a graph, right? And let's call this f of x because, well, that's our most popular function, right? And this is x. And let's say that we had a graph that we knew was from negative infinity was increasing. That is, it has a positive slope, right? Now, it's going to be a non-constant slope. So let's say it's increasing quickly at first. Then it starts to slow down. So you can see that this is definitely going up. So the slope is definitely positive, right? But here it's steeper than here, so it's like it's slowing down. And let's say it slows down so much that suddenly, not too suddenly actually, right? And you'll see why when I say not too suddenly, the slope becomes less than 0, right? Meaning it's decreasing. What happens in between there? Well, if I look at this point, what happens between a positive number, which is getting smaller? So think about this as like 2, 1, 1/2, 1/4, getting closer and closer to 0, because this would mean the slope is 0 here, which in this case corresponds to a maximum, right? And the way we can tell that is that right after that point, the slope is negative. That is, it's decreasing. Now let's say that it's decreasing, and if you look at that, that looks pretty linear, doesn't it? Let's say suddenly that it decides, doing, I'm just going to go off that way, right? Here we are. What has happened? Well, this is one of those spots, if you think about it carefully. What's happening here? We would say the slope is undefined. Why? Well, looking at this, throw an E in there. If I look at this, this has a negative slope, right? That looks pretty linear. Let's say this, at this point the slope is equal to -2. Fair enough? Let's say then, talking about like this area right here. And then let's say that, well, it's hopefully obvious to you that the slope is definitely positive here, right? So this is similar to what went on over here, except it's not kind of smooth. It suddenly just takes that sudden jab, right? So let's say that the slope there is, I don't know, how does positive 2 strike you? That would make sense, right? Going in and going out. So what happens here? Well, that means it's negative 2 here, and then suddenly it jumps to positive 2, meaning it just jumps, and it's not a nice smooth transition where we had a 0 slope happening in between. So that is why it's undefined, and as you may have guessed, that point right there, that's a sharp corner, okay? So, a couple of important distinctions. Slope is the rate of change and can be over a specified interval or at a point. The slope over an interval is called an average. It's called an average rate of change. Slope at a point is called the instantaneous, at this instant, right, rate of change. This even gets a special name called the derivative, which is just code for the instantaneous rate of change. These can be two very different things in the same graph. Let me paint you a picture here. So let's say I was looking at this graph here, and let's say that it represented, let's say a car trip. So let's say that this is distance in miles, right, over time in hours, right? So this is miles, this is hours, and let's say we start from home, right? And then we drive away. We drive away from home. Driving away. And we slow down, and we start driving back towards home, right? Let's say we drive really, really fast towards home, right? Well, maybe we shouldn't drive that fast. That would be a bit weird, wouldn't it? But let's say that we're then driving back towards home, and we slow down, and then we come to a stop, so we stop back at home, right? So what this represents here at time 0, and let's say this is time, I don't know, how does 10 strike you? It really doesn't make a whole lot of difference. What is the average rate of change over the whole trip? So the average rate of change, ROC, right? From 0 to 10 would be, well, the slope using the points here and here. Now if you look at those carefully, that's the point 0, 0. That's the point 10, 0, right? 0, 0, 10, 0. Now if you find the slope there, that, by the way, is going to be 0 minus 0 over 10 minus 0, which equals 0. Well, think about it carefully. The average rate of change is what? Well, did you change over that whole interval? No. So the average rate of change over that whole time is actually nothing. Is that different than, let's say that this is when you hit the store, right? This represents the store. This is the distance to the store here, right? What if that happened at hour 7, right? Let's say you're really dedicated, right? And you want to go shopping. You really must go shopping right there. So that's happening at hour 7. Is there an actual rate of change from 0 to 7? Well, sure. You can designate it in whatever interval you want, right? So that would mean that you're looking at this point. Let's say that that's 100. That sound fair? So that means that point right there is at 7, 100, right? That's one of the points. And the other point is 0, 0. So that means it'd be 100 minus 0 over 7 minus 0, which is 100 divided by 7, which is right around 14, right? Now in the case of this, it'd be 14 miles per hour. You want 100 miles in 7 hours. If you think about it carefully, that better not be very fast. But is that rate of change different than if we change the interval? It gets even better. What if we looked at just this point right here? Could we figure out the slope? And the answer, if we just looked at that point, is no. We'd need another point, wouldn't we? Because in order to find the slope, you have to change. So how could we get it to be an instant? Well, we could pick that point, right? Let's say point at point 1, right? And then maybe we pick a point really close, right there, right? Point 2. If you look at the slope between point 1 and point 2, it's like that. Does that match that graph pretty well? I would say yes, right? So then you could figure out what that slope is. Could that slope be totally different from any of these rates of change? Sure. They're positive here, right? Here it's positive. Wait a second. If you looked over here, though, those rates of change, those slopes, those, in this case, derivatives or instantaneous rate of change, if you want to look at these certain points, they're negative. So you can have a variety of different things happening in a graph at any given time. So high versus low rates of change. This is kind of important. Rate of increase, rate of decrease. Duh. Rate of change up, rate of change down. Okay. Opposite. Going up, going down. Rate of change in steepness. So we know that higher slope means steeper. We know that, steeper graph, higher rate of change. Does not matter if it's an increase or decrease. So this is where we need, it's an English exercise more than anything else. We need to be careful about what's being asked of us or what we're being asked to describe. If we're talking about a high rate of change, it does not matter if it's an increase or decrease. If we're talking about the highest increase, then it must be positive, right? So let's just say for argument's sake we had a graph that looked like, now we've never seen graphs like this. Let's say we had a graph that looked like this, right? So looking at this, do you see places where potentially the rate of change is, what's all this I'm circling? 0, right? So here we'd expect the slope to be 0, right? Okay. Do you see points where the slope is positive? I hope so, right? So here I would say that we're talking this is going up, so the slope is positive here. In this interval, right, this slope is positive here. Here it's going up, so the slope is positive. Versus, you guessed it, negative. Go with this. Slope is negative. It's going down. In fact, it's going all over the place, right? Now, what would you say about some of this? I would argue that if I'm tracing along this graph, if I'm looking like it at this point right here, right, that point seems to be pretty steep, yes? Would we say that that has a higher rate of change than this point? And the answer is yes, right? Now, if I'm looking over here, how about right here, yeah? How would you rate the steepness here versus here? It's kind of hard to say, but I mean, they look like they're almost like the rate of change is about the same, isn't it? But wait, one's positive, one's negative. But the rate of change would still be the same. Unless we're concerned about whether being an increase or decrease, in which case they'd be polar opposites, right? So if I look here, obviously this point right here would have less of a rate of change than this. In fact, I would argue that the highest rate of change in this interval, right, just looking from here to here, that would be the highest rate of change. Why? It's the steepest part of the graph. And if you think about it, if I'm starting off at 0, I got to get up to speed, so it's going to pick up speed, right? Get more and more, in this case, negative, so it's going to get smaller and smaller if you think about what the numbers are going to do, but in reality, they're actually getting faster. Which leads us to the whole absolute value idea. When we take the absolute value, we're talking about distance from 0. It doesn't matter if it's positive or negative, it's just how far apart or how far away it is. Highest rate of change has to do with the absolute value of the rate of change. Okay? Get that to actually square that off, just like that. All right, so that's just a little bit of a teaser. We'll talk a little bit more about this as we move forward.